Hi, in this video we are going to see some basic aspects of sound encoding using numbers. So we've seen that we can represent any kind of information with numbers if we want to use them in a digital system like in a computer. So when we go to represent sound, basically what we do is some discretization both in time and both in the value of the sound. So basically we have a waveform, a sound waveform, a variation of the sound with time. It's a variation of the pressure in the air or the variation of the voltage in the microphone detecting the sound. Okay, and what we do to convert it into digital information is basically to take samples of the sound at regular interval, and this is the first parameter when we convert sound to digital, the sampling rate, the rate at which we take samples, we take values of the intensity of the sound. In a typical sound encoding, we may use something like 44,500 Hz. This is the standard for CD audio quality. Okay, so every second we take more than 44,000 samples, different values, and now every value we convert to a number, to a, for example, an integer number that can be positive or negative, but it's an integer number, and that number we represent with some bits, and it gives us the data resolution. If we use more bits, the number can be more accurate, representing the point in the audio waveform. In the standard CD quality, we use 16 bits. It gives us more than 3,000 possible different values. So every sample will be converted to a number that we can represent with 16 bits. For example, this number here will be something like this, I guess. I don't know if it's correct right now, the right encoding for the number, but the idea is that I take the number and represented this number with 16 bits. Okay, so in the end we have converted our sound in a sequence of bits in small packets of 16 bits. If we have typical audio has two channels. This is stereo, one channel for the right ear, another channel for the left ear. So we may have not one waveform but two waveforms. So we do it twice, once for every wave that we want to encode, would be the stereo signal. Okay, so this is the basic sound encoding parameter: the sampling rate, how long the data resolution, which is how many with the precision we represent every sample, and the number of channels that we want to encode. As I said, these are the typical values for CD, the standard CD audio quality. So the if we want to make calculations about some typical calculations when we have some kind of sound encoded, is the data size, how much data I have to store, measured normally in bytes or megabytes or something like that, the time that we have encoded, how long does the sound is, and the data rate. The data rate is how much data I have per unit of encoded time. Okay, so the data rate is actually the size divided by the time, or the size is the data rate times the encoded time. Okay, this is general. This actually can be applied to sound, to video fragment as well. In typical sound formats we use some kind of compression, but when we do not use compression, I mean when we take the samples and generate the numbers and just store the numbers as is without compression, the data rate can be derived from the sound quality parameters. It's basically the data rate is calculated like that because the data resolution is how much data I have per sample. The number of channels I multiply, so I have the data per sample in all the channels. And if I multiply by the sampling rate is basically the data rate measured in samples per unit of time, per second. Okay, so this will give us how much data I have per second. The key on compression is that when we compress the audio, we find ways to store the same signal with smaller numbers. A very basic compression technique consists on storing this number with less than 16 bits. Let's say, for example, if you see from one sample to the next one, okay, the variation used to be not very big. So one of the most basic compression techniques is not to store the whole samples, but to store only the variations. We may use 16 bits to store a complete sample, okay, but because variations are smaller, are typically smaller, we can use only 8 bits, for example, to store these differences. So our sequence, instead of being a sequence of 16 bits, 16 bits, 16 bits, 16 bits, I can store one full sample and then just the variations, okay, using fewer bits. It means that we are going to use less data, okay. With this kind of basic compression techniques, we can still represent the curve exactly, because I can then take the full value and add the increments, and we can recover the wave exactly as it were. This type of algorithms is called lossless compression algorithm, because you don't sacrifice the quality. You can recover the exact curve, only that you apply some technique to save some bits. Typical lossless quality algorithms like FLAC, for example, may save half of the size of the recording. But there are other algorithms that compress more, but changing the waveform a little bit. Some of these algorithms use more complex techniques based on the sound perception algorithms, like, for example, MP3 or Vorbis or many others, AAC, like used in radio recordings. And by assuming the loss of some quality, they can compress audio much more, like to 1/10 of the original size, without losing much quality. So in the assignments you have some exercises related to sound encoding. Basically, you have an exercise, a simple exercise to calculate the data rate of a CD quality recording. You are asked to calculate it in kilobits per second. Okay, as I told you, basically the sampling frequency is the data rate in samples per second. So in knowing all the data, you can calculate the data rate as given in these slides. And once we have this, we can calculate the size. In this case, it's this unit, you remember, is megabytes. The size in megabytes of recording that is 3 minutes and 52 seconds long. This is a typical size for a song. So you can use the data rate calculated above. So basically, once you calculate the data rate, you calculate the length by taking the data rate and multiplying it by the time. Okay. The difficulty here is more to make the necessary unit conversion. Okay. And to do this exercise, here you have the standard audio encoding parameters for CD quality audio. Okay, another case is this one, so that you can compare with an actual recording. It's similar, but it's about taking some audio clip you have, like a song or something that is about 4 minutes long. You take the song in some compressed format. It's just to see that compressed format actually compress the sound, and you can generate the sound in the uncompressed way, and then you can see that when the audio is not compressed, the size can be calculated using the parameters. Okay. So this exercise, what it tells you is that you can calculate the data rate of the compressed audio by dividing the size of your clip by the duration. Okay, you have this data rate. It will be the compressed data rate, the size of the MP3 file divided by the time. Okay, then you can take this audio clip and convert to the standard CD quality format. You can use a audio conversion tool like Audacity, and to do so you can open your MP3 audio file and use Audacity to convert it or to encode it in PCM format. PCM is the pulse coding modulation, the basic format I've explained in the slides, and use this PCM format using 44,100 Hz samples per second, 16 bits, 2 channels. So be sure to use this format for your audio, and then you can save it in an uncompressed format like a WAV file, WAV file. Okay, so then you can see the size of the file, and you can compare with the expected raw size of your audio, calculated as in exercise 7. So the raw size will be the uncompressed data rate is the sampling frequency times the sample size times the number of channels. Okay, this is the uncompressed data rate, and so the length, the uncompressed length of your audio will be your uncompressed data rate times the duration of the audio. So because this file format is uncompressed, okay, this result here should be similar to the actual size of the file. Okay, so it's something that you can check to see that these calculations correspond to real size, but it's not easy to see because most of the time we use some kind of compression on audio. So that's it. Thank you.